Hello everyone, my name is Yunkai Li and welcome to our presentation. Today I'm excited to present our project on melanoma image classification. Through this experiment, we aim to design a system that can distinguish between different states of skin disease. And here is our contents. We divided this project into 6 parts. Now let me introduce them one by one. Here's the first part, the significance and objectives. Melanoma is a severe form of skin cancer. The patient will benefit from early detection and treatment, so their survival rate will be improved significantly. However, traditional diagnosis always rely on visual inspections by doctor and biopsies. So it often faces challenges like time consumption and bias. Our project aims to harness the power of the ResNet-50 model to improve melanoma classification. It is a binary classification system which is more accurate, and we believe that it will reduce misdiagnosis and accurate the determining process. So here's the second part, the environment configuration. In this experiment, we use PyTorch and Anaconda toolkit to set up our environment. Now, let me introduce the model we use in this experiment, the ResNet-50. But before introducing the structure and efficiency of the ResNet, I want to make a comparison between VGG, the Visual Geometry Group, and the ResNet. VGG model is easier to understand and implement due to its simple linear structure, but it usually requires more data for effective training to avoid overfitting. VGG models have a higher number of parameters, which may lead to easier overfitting when the dataset is small, and this feature will lead to a serious problem in medical diagnosis, where data can be scarce, especially for rare disease. So VGG might not perform well because it doesn't have enough examples to learn from. The ResNet is designed to perform deep learning tasks with fewer layers and fewer parameters. This is beneficial in medicine where datasets are smaller. Here's the structure of the ResNet-50. The ResNet-50 network is a deep residual network consisting of 50 layers, using a series of residual blocks. These blocks are the core of the network's structure. The first part of the structure is initial convolution and pooling layer. The network starts with a 7×7 convolutional layer with a stride of 2, followed by a max pooling layer. This configuration helps reduce feature dimensions while preserving essential information. The second part is the residual blocks. Several residual blocks follow, each containing 3 convolutional layers. The first and third layers typically use 1×1 convolution kernels to reduce and increase dimensions, respectively, while the middle layer uses a 3×3 convolution kernel for feature extraction. The third part is the skip connection. Skip connections in each residual block allow input to jump across one or more convolutional layers to the output of the block, facilitating information transfer within the network and preventing signal attenuation. And here comes the fully connected layer. The network concludes with an average pooling layer followed by a fully connected layer that outputs the final classification results. So what is the innovation of the ResNet-50? The core innovation of ResNet-50 is its introduction of the residual learning framework. In traditional deep networks, increasing the number of layers often leads to worse training outcomes. That is mainly due to the vanishing or the exploding of the gradients. ResNet addresses this by incorporating residual blocks that allow direct gradient transfer between layers. The residual blocks enable input to be processed through one or more convolutional layers. with the input directly added to the output of the convolutional layer via skip connection. This design means the network learns the residual output between layers, simplifying the learning process and solving the problem of vanishing ingredients. Also, the ResNet 50 has excellent efficiency. The ResNet 50 model trains and infers very quickly. This efficiency is due to its residual connection design, which allows for fewer training iterations to achieve convergence. Additionally, current hardware and deep learning frameworks offer strong optimization support for convolutional networks, further enhancing the operational efficiency of ResNet 50. Next, my classmate Tao Wu will introduce the dataset.
Okay, now let me introduce the dataset. Okay, we are here to discuss a large set of images that can help doctors show if someone has skin problems, such as melanoma or kinds of skin cancers. Those data are from the EECE challenge dataset. The picture has two parts. Each one is super clean and see that if someone is okay, we call them benign, and if it might be bad, which we call is malignant. But we can't really tell the difference with the naked eyes. Look at these. The other one. Each picture like this one has much note tell us what it is benign. And in the test date, we use the 0 for the benign and 1 for that could be malignant. It is very good for machine to do the classification. Next, we will discuss how we do it. Introduction to the code declarations. Areas.py shows the value arguments used for the training and testing, and create dataset.py. This script is used to reading and the date in the JSON. And the dategen.py, the script is used for the dataset examinations as well as date enhancement and the data loading. And min.py, context training, evaluations, and testing. And the roast.py is a rewrite of the ResNet for various type of networkings. Step 1, loading date. We use the transformation to get the picture ready, like make them all the same size. We make groups of pictures for training and checking our work, called transit and value set. Then we put those pictures into train loaders and value loaders, which help us look at many pictures at once and mix them up to teach the computer better. Step 2, build the models. As we all know, it's very difficult for computer to use the CPU, so we need to use the GPU to train the image date. So we need to use the CUDA. That's why we choose the PayCharm to develop this project. The optimizer is defined by the gate functions will control how the models is updated and based on the date sims and the loose function. Finally, the scheduler is set to adjust the linear rent as the model is trained, which is help to achieve performance. Step 3, model training and evaluations. Training the models. The code does same steps over and over. Each step is called an eCOP. Each eCOP is like a complete running. use the old date, it show you what step you are on, and the learning rate, which is just sitting and the chance how quickly the models gets better. And the elevation, the models for after each step, the code looks like two things: the loss, the occurrence. Occurrence is the percent of times the models get things right. The more, the better. Adjusting the learning rate. If the model isn't getting better, there are parts of code that trends to help by changing the learner rate. Finally, we have to save the models. If the model does it better so far, the code keep it. Then that way you can use those good models later. In the picture, we can see we train the 200 pictures for 10,000 times. Now let me show you the results. The accuracy is 0.9, means the models gets right 9% of the times, and the confused Mary try is a label that helps see how well the model did different contrasts. The numbers that in the table tell us if the model did a good job or bad. Then there are some numbers called recall, F1 scores, and the supports. It means how good the model is. The higher scores means the better models. And the ROC scores is also the 0.9. Another way is to judge how well the model works. The closer to the one is the better. So our model is very better from those numbers. And this is the result. We show the amalgamate image. The image is the classification in the amalgamate, and the benign image shows the benign. That's all. Thank you.